Hello, chemistry. Here we are starting section 3 of chapter 22, page 696. And we have been so far talking about just carbon and hydrogen, hydrocarbons, saturated, unsaturated, and so forth. And we are just barely scratching the surface. And now we're going to talk about what's called functional groups. Again, it's just going to be sort of an intro. There is so much to learn about this. You can take entire classes and majors in college on this chapter. So, what's a functional group? A functional group is an atom or group of atoms that is responsible for the specific properties of the organic compound. And we're going to have a whole table here of them, and what we go through, I may be able to say fast enough, but it may not be something that you can completely absorb. And you may want to slow down the video. You may want to watch it again and to try to absorb it. You may not catch it all the first go here. So here's some examples that our textbook gives us in this table. All of these have 4 carbons. If they have 4 carbons, what's the root of the base name? And that's bute. And this is butane. It's an alkane, all single bonds. Then if we took off one of those hydrogens and attached a OH group to it, we would turn it into what's called an alcohol. An alcohol is anything that has an OH attached to it like this. Now, don't get this confused with a hydroxide ion. This is not an ion. This is a covalent bond, and it's an alcohol group, we call it, and it can get attached to a hydrocarbon, really just about any carbon. So here's an example of butanol. There you see the 4 carbons. Now you see it sticking out this way. It doesn't have to stick out that way necessarily because this guy can rotate. Remember, he can rotate, so we can draw it on any hydrogen direction we want to. Notice that the name of it is 1-butanol. What's the 1 telling us? That the oxygen is attached to the first carbon. So what would we call it if we were to take this and put it here on the molecule? Well, that would be called 2-butanol. What if we put it here? It would be called 2-butanol. This would be called also 2-butanol because we could turn it this way and you go 1,2. So really we have only 2 options, a 1-butanol or a 2-butanol. Now we could put more alcohols on there so that we could have a 2,2-butanol or a 1,2-butanol. We could get lots of different kinds of alcohol. So over here on your textbook page, it starts talking about alcohols, the first of the different compounds in the table. Now, alcohols are anything that have the OH group attached, and then if we name it an alcohol like butane with the OH group on it, we just add the OL to the name, so it becomes butanol, propanol, pentanol, hexanol, whatever. We just put the ol on it. There is a 3-carbon molecule, which if it just had 3, we would call it propane or whatever. If we add a alcohol group to it, we would now call it propanol. But if we put on there 3 groups, it becomes propane triol. Tri meaning 3 alcohol groups on it. So this is the molecule right here. It also has a more familiar name to some of you have probably heard of, glycerol. It's used in anything from lipstick to lotion and things like this to try to keep your skin from drying out. So we have 3 alcohols on 1, 2, 3 carbons. Now, one of the bad things about alcohols is they have hydrogen bonding the same way that water has hydrogen bonding. Remember, the oxygen is a little bit negative and the hydrogen is a little bit positive. So what can happen is, then one reason why it'll keep you moist is that this hydrogen and the oxygen, they get attracted to each other, and so that holds on to the water, holds on to the moisture, which is good if you're making lotion. But one of the things that's made for our gasoline these days is ethanol. You've probably heard ethanol is in our gasoline now, and there are good things about that and there are bad things about that. The good thing about it is that ethanol, is a renewable resource. It can be grown and made, whether it be, sugarcane or corn. In fact, in the United States, we have required that 10% of our fuel that goes into your car has to be ethanol. Well, that's good, and it's bad. And one of the good things about it is, yes, it's renewable, but the bad thing about it is that, here we go, ethanol looks kind of like a little doggy. And one of the bad things about it is, just like with the glycerol, it attracts the water molecule. And when it does that, that's bad for the gasoline. Do we want water in the gas? Water doesn't burn. And so what can happen is the ethanol in the gasoline can be attracted to a gasoline molecule, because like attracts like, but it can also attract the water molecule, which it can be two-phased. Attracted to a nonpolar molecule and attracted to a polar molecule. So now there's products that you can buy that will, what's called, stabilize your fuel. Like if you're on a boat or things like this, you really don't want your fuel to have a little bit of water in it, so you can put additives to try to keep the water from being a problem. But that's one of the challenges of having ethanol in our gasoline. It's also the same molecule that is in beer and wine and vodka and so forth, is this ethanol. And all alcohol is poisonous. It's just some is more poisonous than other alcohols. This one is not as poisonous, so you can consume some of it and it doesn't knock you dead. But obviously, if you probably all know that if you drink enough of it in one time, it will kill you. And alcohol slowly does destroy you and your liver, your brain cells and so forth. And as time goes on, your liver continuing to try to detoxify you from this molecule will get harder and harder, and we call that cirrhosis of the liver. And eventually you'll require a liver transplant. It's the number one, I think it's one of the number one transplants that are needed in the United States is liver transplant, and the number one reason is from too much alcohol or drinking alcohol and so forth. So some other things about ethanol is it has about 60% the energy of gasoline. So if you have a gallon of gasoline compared to a gallon of ethanol, this has much less energy, so it's not going to take your car as far. The good thing is you can grow it again with the corn or the sugarcane and so forth, whereas the gasoline, we pump it out of the ground. Once we've done that, it's gone. So this is renewable. It will absorb the carbon and so forth and have less emissions in that way. So that's good, but it does have less energy per gallon. Our next part here is to talk about alkyl halides. Alkyl halides simply are organic compounds with one or more halogens. Who are the halogens? That's group 17, fluorine, chlorine, bromine, and iodine. So it's one of the few functional groups here that are in your table that is not just carbon, hydrogen, and oxygen. It's actually got fluorine, chlorine, bromine, and iodine. So here's one example. This would be methane, and here we've attached one halogen here. And so let's say that this is chlorine. This would be chloromethane. Chloromethane. And we could make larger molecules, smaller molecules. All you have to do is attach a chlorine or fluorine to it. Now notice that it has sort of a generic formula. Whenever we write the R in these formulas, we're talking about just a carbon or many carbons. So we could take a molecule like this. Here's the R for this molecule. We could just put it on here. And now this is the R. This is the R that that's referring to. It just means some unknown number of carbon atoms that are following the functional group. So that's the alkyl halides. Your textbook talks about one of the most famous ones is freon, which is also called chlorofluorocarbons, because it has 2 or 3 chlorines for a carbon. So this is here one with just one. Here there's 3 chlorines and 1 fluorine. So it's called CFCs. They were very popular to use in propellants for like hairspray or anything that you wanted to squirt out of a can, paint, things like this. It works so well. But we discovered that it destroys the atmosphere, that is the ozone. And what happens is the chlorofluoromethanes with sunlight break down and the chlorine busts off of there. That chlorine comes to the ozone. Ozone is O3 and knocks out an oxygen and leaves it with O2. Well, you might say, well, O2, that's what I breathe. That's good. Well, we do need O2, but up in the sky, way up high, we want the ozone because the ozone helps filter out the ultraviolet light to keep us from getting sunburned and skin cancer and so forth. So the less ozone we have, the more ultraviolet light, the more damage we get to our skin. And the other concern about this is that this molecule can move on, grab another oxygen, and knock it off so that it becomes O2. Again, you might say, oh, that's good, I need that. But this chlorine goes back into this process and does this again and again, and it could destroy up to thousands of molecules. And so in 1987, Mr. Singer was starting college. At that time, they signed an agreement, 100 nations, that they were going to reduce to try to eliminate CFCs. We haven't completely eliminated them. A lot of refrigerators, air conditioners, your car, air conditioners and so forth still use these because they work so well. And it is actually even used in some agriculture for fungicides and so forth, and it's legally done so. Another alkyl halide, that is a carbon group with fluorine in this case attached to it, a halogen, is a long material, long chains, and that's called Teflon. Teflon is this non-stick surface that gets attached to frying pans and many other things so that things don't stick. It can be used in industry and so forth, and that is an application of using fluorine with a carbon atom. The next functional group that our book talks about is ethers. Ethers are interesting in that they have an oxygen and you have an R group on each side. Now, they say R and R prime to try to distinguish that these R's do not have to be the same. They can be different. So it just barely mentions it right here at the bottom of this page. This is the formula ROR, and these tend to be not very reactive, and they're often used as solvents. That means they dissolve other things. And just to illustrate this, here's a R group, just some random number of carbons. We're going to attach an oxygen to him, and then we have to attach another R group. So I just chose to be 1 carbon, and this would be an ether, an oxygen with 2 carbon things attached and going off in different directions. Okay, the next one is going to be an aldehyde. Aldehyde is somewhat similar in that it has oxygen, and there's 2 kinds of these that are so similar. There's the aldehyde and there's the ketone. Both of them may look the same at the beginning, but see here you have carbon attached to oxygen, double bonded. Over here, you can see that we have an R group on the left side, or on one side, and over here we have another R group, or we could have just a hydrogen. If it has just a hydrogen, then it's called an aldehyde. If it has another carbon, then it's called a ketone. But otherwise, they're basically the same. So here's an example of a aldehyde. You have an R group, you have the double bonded oxygen, and then you have a hydrogen coming off that side. This would be an aldehyde. Now the difference between an aldehyde and a ketone is the ketone has, instead of the hydrogen, it has another carbon. So we could take any other kind of R group, carbon group, and attach it to it, and now that becomes a new aldehyde. So this has a double bond, and then R groups on each side. Notice that it's R and R prime, whereas back here it was the hydrogen. Now, here we have a little bit more in your book. What's interesting is that aldehydes and ketones often make odors and flavors that come from these two groups. And here are some examples from a flower, from cinnamon, from raspberries, vanilla, benzaldehyde. These are things that you could say, what does that smell like? And you have an idea what it smells like. Both of them have a group that we call a carbonyl group. It's the same thing here. One ends with an H, one ends with an R. All right, so now we're going to go on to amines. This is the one other that has something besides carbon, hydrogen, and oxygen. We had the halogens, and now we have the amines. Amines in our table are where we have a nitrogen, and a nitrogen is the center of a bunch of R groups. And this really has a very similar arrangement as does ammonia. And these make often great fertilizers. So let's see what an amine looks like. Here's a model of it. I'm going to put this on here because this is to represent the unbonded lone pair electrons that are on the nitrogen. The blue is the nitrogen, the black are the carbons. We have 3 different R groups attached, and this makes this an amine. So we call this a derivative of ammonia. For the last part of our section, we're going to talk about carboxylic acids and esters. Now, part of the fun thing is we've got ether and ester. We need to think about those things differently. A carboxylic acid and an ester are related in that they have the same layout, except for just like the aldehydes and ketones. Here we have a H after the O, and here we get in another R group. So let's take a look at what that looks like. So here is a carboxylic acid. You might remember a long time ago we've talked about CH3COOH, vinegar, acetic acid, and that is drawn like that. Now, here is a model of that. You see, here's our CH3 right here, and here is our COOH. This is the hydrogen that wants to come off and make it into a acid because it would increase the hydrogen ion concentration. That's why it's called a carboxylic acid. Now, we could add more carbons on here if we wanted to by taking off a hydrogen and put another carbon on here. So this would be propanoic acid because it's got 3 carbons and we've got the carboxylic group on here. Now, the difference between a carboxylic acid and an ester is that instead of this hydrogen, we can put on another R group. So we're going to add this guy to here and take off the hydrogen. And by so doing, we have turned it from a carboxylic acid, because it can't be an acid anymore. Can't lose a hydrogen, and turn it into a ester. And this is where it gets a little bit fun because a lot of them have oxygen in them. Here we have oxygen in the middle, and that's an ether. And here we have oxygen in the middle, but keep in mind there's another oxygen over here. For ether, there's only 1 oxygen involved. For an ester, there's 2 oxygens involved. And figuring out which one is which and memorizing that is important. You will need to know each one of these for the test. So, I encourage you to study these, practice them, listen to the presentation. We're also going to do a little model lab on this to help you understand that. We also want to point out and mention that citric acid is a carboxylic acid. So here was our carboxylic acid. Instead of having just one of these, it has three of them. Now, the graphics in the textbook got a little bit messed up, so I redrew it here. You've got a carbon that goes off to one carboxylic acid, two carboxylic acid, three carboxylic acid. So you can understand how citric acid is a little more acidic than vinegar in that you've got three of them here willing to kick off the hydrogens and form an acid. So you've got this carbon here with three carboxylic acids on it, and that's called citric acid. All right, that concludes our section 22-3. And we'll move on to section 4 coming up soon.